Hello students, welcome to JCE Connect series of lectures. So fluid dynamics is module number 3. So in previous module, that is in module number 1, where we have been restricted our study only for a fluid at rest. So now we turn our attention to fluids in motion. So that is what we call as a fluid dynamics. The fluid dynamics is nothing but the study of fluid in motion where the forces are taken into account, that is the forces which are responsible for the motion of fluid. Those are to be taken into account for the analysis purpose. So here in this particular chapter, instead of trying to study the motion of fluid particle, means the each and every particle, instead of the taking a fluid particle, each particle of the fluid as a function of time. So here we are describe the properties of a moving fluid at each point as a function of time. Okay, so as a function of time. So let us discuss about the flow characteristics. Since we are studying the fluid dynamics, so we need to understand the flow characteristics of the fluid. So whenever a fluid is in a motion like this, whenever a fluid is in motion, its flow can be characterized as being one of the two types. So the flow is said to be steady or laminar. So this type of flow, what we call as a laminar flow or a streamline flow, if each particle of the fluid follows a smooth path such that the paths of different particles never ever cross each other, as shown in this picture here. So in steady flow, the velocity of the fluid at any point, remains constant in time. Means the velocity of this fluid particle will never change with respect to the time. It will be a constant. That is what we call as a steady flow. So a laminar flow or a streamline flow, or you can call it as a steady flow. And this fluid motion will be having a certain velocity. It will be having a certain velocity. If this velocity exceeds certain limit, that is above a certain critical speed, the fluid flow becomes a turbulent. So fluid flow will become a turbulent. So like this. So this is a turbulent flow where the fluid particles are not moving in a systematic manner. They are moving in a haphazard manner. They are called as a turbulent flow. So the turbulent flow is irregular flow characterized by a small whirlpool like regions. So that is shown in this figure. And also the term viscosity is commonly used in the description of fluid flow to characterize the degree of internal fluid friction in a fluid mass. So this internal friction or a viscous force, internal friction or the viscous force, is associated with the resistance that two adjacent layers of fluid have to moving relative to each other. So the viscosity causes part of the kinetic energy of a fluid to be converted to internal energy. So this mechanism is similar to one by which an object sliding on a rough horizontal surface loses kinetic energy. So this is also a turbulent flow. So look at this picture here. In this picture, a laminar flow around an automobile in a test wind tunnel. So this is the air particles. So this will be in a streamline flow. So the air is passing while testing this automobile. So that is, car is testing in a wind tunnel, and this air motion, what we call as a laminar flow. Okay. Even a hot gases from a cigarette. See, look at this picture. A hot gases from a cigarette made visible by a smoke particle. See, look here. This is a smoke particle. So here, see, look at this picture. Hot gases from a cigarette made visible by a smoke particle. So the smoke first moves in a laminar flow at the bottom and then in a turbulent flow above. So initially this flow we call as a laminar, means all the gas particles are moving in a order like this. So they are like this, they are moving. Then later they all get mixed up like this. So this is what we call as a turbulent flow. Okay, turbulent flow. So now, because of the motion of real fluids, the motion of real fluids is very complex, so and not fully understood, we make some simplifying assumptions in our approach. Means to analyze real fluids, so we need to make certain assumptions. So in our model of an ideal fluid, we make the following 4 assumptions for ideal fluid. So for ideal fluid, so the fluid is ideal means the viscosity is 0. So fluid is ideal means the viscosity is 0, or it is called as the fluid is a non-viscous. So in a non-viscous fluid, internal friction is neglected here. So all fluids will be having certain viscosity, but we're assuming the fluid as a ideal, that is non-viscous. So in a non-viscous fluid, internal fluid is neglected. An object moving through the fluid experiences no viscous force. And the second assumption is the flow is steady. Means in a steady, or it is also called as a laminar flow, the velocity of the fluid at each point remains constant. That is what we call as a steady flow. Just it is an assumption, but practically it is not possible. So for analysis purpose, we are making certain assumptions here. And the third one is the flow is incompressible, that is fluid is incompressible. So means the density of an incompressible fluid is constant. Density remains constant. And next is the flow is irrotational. Means in irrotational flow, the fluid has no angular momentum about any point. So if a small paddle wheel placed anywhere in the fluid does not rotate about the wheel's center of mass, then the flow is irrotational. So these are the 4 assumptions made in a fluid dynamics for the analysis of fluid motion. Streamlines and the equation of continuity. The path taken by a fluid particle under a steady flow is called as streamline. The velocity of the particle is always tangent to the streamline as shown in figure like this, and a set of streamlines like ones shown in this figure form a tube of flow that is called as a stream tube. So note that the fluid particles cannot flow into or out of the sides of the tube. If they could, then the streamline would cross each other. So in this particular flow, so we call it as a streamline flow. That is, the path taken by a fluid particle under a steady flow is called as a streamline. The group of streamlines are called as a stream tube, and the velocity at any point, velocity of a particle at any point is always tangent to the streamline. So if you draw a tangent to the streamline, and that represents the velocity of that particle always. Now, equation of continuity. So let us consider an ideal fluid flowing through a pipe of non-uniform size as shown in this figure. So look at this pipe of non-uniform size. It's not a uniform, so it's a variable duct. An ideal fluid is flowing through this pipe. Then the particle in the fluid move along the streamlines like this. The particles in the fluid move along the streamlines in a steady flow. Then in a time t, the fluid at the end of the pipe moves a distance delta x1. That is, in a time t, the fluid at the bottom end of the pipe moves at a distance x1, delta x1, so which can be written as delta x1 equal to, so velocity multiplied by time. As we know, the formula for velocity is distance by time, so the distance equal to what? Velocity multiplied by time. Since we are considered at section 1, so it is written as v1, and also the distance traveled by the fluid particle as delta x1. So you can look at this animated picture here. So all the fluid particles are passing at a particular cross section. They are moving in this direction. So here we have considered an ideal fluid flowing through a pipe of non-uniform size, and the particles in the fluid move along the streamlines. The particles in the fluid, they are moving along the streamline, so in a steady flow. So in a time t, the fluid at the bottom end of the pipe, see here at the bottom end of the pipe, moves a distance delta x1, which is equal to v1 into t. v1 into t. Suppose if A1 is the cross-sectional area in this region, then the mass of the fluid contained in the left shaded region is, that is, mass of fluid m1 equal to, here mass of fluid m1 equal to rho A1 into delta x1. So mass, as we know, density equal to mass by volume. Density is equal to what? Mass by volume. So mass equal to what? Density multiplied by volume. So it's a density multiplied by, this is the volume, area into the distance, area into length. Okay, So area into length will be what? The mass. So which can be written as rho A1 into V1 into T, because delta x1 is what? V1 into T, this one. Okay. So where the rho is the, that is density of the ideal fluid, which is a non-changing quantity, density of the ideal fluid. Similarly, the fluid that moves through the upper end of the pipe here, similarly here you can take the fluid that moves through the upper end of the pipe in the time t has a mass m2 here at this region. At this region, the fluid is passing at this region. The mass here will be what? Rho A2 V2 into T. Okay. Then, however, because mass is conserved and because the flow is steady, the mass that crosses A1, that is cross-sectional area A1 here the mass is conserved and also the flow is steady. The mass that crosses A1 in time t must equals the mass that crosses A2 in time t, that is m1 equal to m2, because of law of conservation of mass. Or you can say rho A1 V1 T is equal to rho A2 V2 into T. This means that A1 V1 is equal to A2 V2 is equal to constant. So here density get cancels both side, again time get cancels, then finally we get A1 V1 equal to A2 V2 equal to constant. So this expression is called as equation of continuity, and it states that the product of the area and the fluid speed, see look here, the product of the area and the fluid speed at all points along the pipe is a constant for an incompressible fluid. I'll repeat. So this equation, this one, A1 V1 equal to A2 V2 is equal to constant, means the product of the area and the fluid speed at all points along the pipe is a constant for an incompressible fluid. See, along this pipe, along this line, the continuity equation, that is A1 V1 equal to A2 V2 equal to constant. And this equation, see this above equation, what it tells. So this above equation, what it tells, this equation tells us that the speed is high where the tube is constricted. Look at this picture here, where the tube is constricted, means the very narrow, or the can call it as a small, the velocity is very high here. That is, the equation tells that the speed of the fluid particle is very high where the tube is constricted or narrow, and the low where the tube is wide or large. See, at this region, if you take, the fluid will be having a low velocity, and at this region the fluid particle will be having a very high velocity. So what this equation tells, wherever the area is small, the velocity is high, and wherever the area is more, the velocity is low. That is, the product A into V, which has the dimensions of volume per unit time, that is area unit is what? Meter square, and velocity is meter per second, then meter into meter square, meter cube per second. So this it has a volume per unit time and is called either the volume flux or the flow rate. So the condition A into V is equal to constant is equal to the statement that the volume of fluid that enters one end of the tube in a given time interval equals the volume leaving the other end of the tube in the same time interval if no leaks are present. So this is what we call as a equation of continuity. So the flow in is equal to the flow out. Okay, so this is what we call as a equation of continuity. A1 V1 is equal to A2 V2. And here a fluid moving with a steady flow through a pipe of varying cross-sectional area. Here a fluid moving with a steady flow through a pipe of varying cross-sectional area. The volume of fluid flowing through a area A1 in a time interval T must be equal to the volume of flowing through area A2 in the same time interval. So therefore A1 V1 is equal to A2 V2. So this is about the equation of continuity, and this equation is very useful in a fluid dynamics. It is very useful for solving the fluid problems. So you have to remember, wherever the area is small, there the velocity is high. Wherever the area is large, the velocity is less. So you can write, so velocity is inversely proportional to, here you can write velocity is inversely proportional to cross-sectional area. So that is continuity equation. So whenever the area is more, velocity will be less. Whenever the area is less, velocity will be more. So this is continuity equation, that is written here. Area A increases, speed V decreases. Area A increases, the speed, that is velocity, decreases. So this is equation of continuity. Thank you.